Hello everyone, I'm very glad to participate in the 2020 MariaDB Fest conference. My Chinese name is Pengfei and my English name is Matt, the product manager of Watch Technology. I'm responsible for the product design of cloud native database. Currently, the product has deployed more than 400 nodes in private and public cloud environment. Today, my topic is MariaDB database clusters on Kubernetes. The challenges of MariaDB database clusters on cloud we have been met as following list. First, network solution of hundreds and thousands MariaDB instances over multi-data centers. The most complex part of the public cloud is the network solution. It involves the deployment and scheduling MariaDB instance over multi-data centers. Fortunately, Kubernetes has provided mature and stable network solutions, such as Calico and Frano. Second, cost-effective computing resource. Because each server node runs many MariaDB instances together, the CPU, the memory resources required for all MariaDB instances in a server more than the hardware limitation. Third, portability and easy scale-out. MariaDB clusters be able to deploy multi-released operating system like Red Hat, Ubuntu, Linux, and easy to scale out the MariaDB cluster instance and the server nodes. Fourth, self-healing and auto failover. Because it is impossible to manually operate and maintain huge numbers of MariaDB on cloud. It needs self-healing capabilities such as offline failed MariaDB instance and online new one replaced. Fifth, save disk space. Software and applications are built by Docker engine into image as a running container on Kubernetes. Multi-MariaDB instance running in a server can ensure the best images due to the Docker storage driver. So let's take a side of Kubernetes architecture. The Kubernetes architecture departs into the control panel and the work node panel. In control panel, it has three components: API server, scheduler, and the controller manager. On the work node side, as a Kubernetes and the proxy, we usually use the Docker engine as our container runtime. Both of the components only interact with the API server. We can use the kubectl command to apply the YAML file to tell API server how to deploy our resource, and all the metadata is stored in the etcd. And in Kubernetes, there has so many built-in objects, and it provides powerful resource management. For example, we can use deployment to deploy stateless applications such as PHP admin and MaxScale. If MaxScale becomes computing bottleneck, we can quickly add a replicas number to improve throughput. Demo set used to deploy system component such as the Calico, because the Calico needed to run in each node to allocate IP address for every path. Stateful set. Stateful set is to deploy stateful service such as MariaDB, the MySQL database. It requires that each pod bound with the PV to persist the data. The job is task management. We can perform a backup task for MariaDB clusters, like the cron job or once backup job. The service can automatically discover backend MariaDB instance in Kubernetes and do load balancer. So let's take a look at an example of using Server Set to create a MariaDB instance. This is a demo YAML file of Server Set. The advantages of creating pods with Server Set is that each pod has its own PV, and the name of each pod will be prefixed with the metadata field name defined, and plus order the number from 0. For example, the first replica named MariaDB 01, second named MariaDB 02. The YAML file also includes the container image version, the Docker registry address, the storage class. The storage class provides the PV volume, and specific the directory with the PV mount. When a pod to be scheduled, the Server Set will create a new pod to replace, but it retains the original name, network identifier, and the bound PV volume to maintain the pod state. The controller workflow is shown like this. First of all, we preparing a YAML file contain Server Set manifest, and through the Kubernetes control, applying it to API server. The controller manager, Server Set is one of the controller manager, by the way. The Server Set controller lists the list of API servers newly resourced and create pod manifest. Newly created pods now stored in etcd. The scheduler chooses the best node for the pod assigned to the node. The Kubernetes watch API server and see a new pod scheduled to its node. It tells Docker, the Docker engine, to run containers. Okay. We use Server Set to deploy a single instance of MariaDB so far, which has certain fault tolerance. However, MariaDB clusters on production environment need high availability, like MariaDB master slave or Galera cluster solutions. The backup strategy, the automatic do the backup and the recovery of the MariaDB instance. Monitoring the running database metrics, the read-write split. I use the proxy, the max scale to the read-write split. On rolling update, as the MariaDB official released the patch, we needed to do it. Agility means the MariaDB clusters and the server nodes are easy to scale out when we needed more computing and storages. All above features we can be achieved by extending Kubernetes API. We can customize the API objects interaction with a specific controller. For example, the extended API object is named MariaDB Cluster. It tells Kubernetes that our MariaDB cluster is composed of 2 MariaDB HA instances and 2 read-only slave instances. The controller inside Kubernetes regularly compares the current MariaDB instance running state with our expected state, and find out that there's only one read-only instance running, so the controller would create a new MariaDB instance according to the logical we defined to start a new pod for MariaDB slave, configure MariaDB slave replications to the master, and do the data balance. And the pseudocode is like this. There has a for cycle, and the get desired state function returned our expected desired desired, get the current state function, return the current running status. The recancel function will compare the desired and the current status and do our logical. So the MariaDB cluster controller is like this. We have already extended the API of the MariaDB cluster into the etcd, and we're preparing a YAML file. The YAML file contains MariaDB cluster manifest, and through the Kubernetes control, apply it to the API server. Once we have our specific MariaDB cluster controller, the MariaDB cluster controller manager list of API servers newly resourced and create a related stateful set manifest. And the stateful set controller will notification through the watch and create the pod and the workflow we have mentioned before. The MariaDB cluster controller, we create two stateful sets. One stateful set, the metadata name is MariaDB HA, labeled DB role HA. And another stateful set named MariaDB slave, labeled DB role slave, and the spec the replicas number is 2. And each stateful set exports the service to adjust the backend MariaDB IP. In front of the MariaDB clusters, you can use the Kubernetes deployment to deploy the stateless proxy max scale and configure the master and the slave address on the max scale configure file with the name of the two stateful sets. Expose the service respectively. So we can get a MariaDB cluster. We can get a MariaDB clusters composed of two MariaDB HA to MariaDB slave using the max scale proxy to carry out read-write split. And let's take a look at the MariaDB cluster internal. Kubernetes pod is the basic scheduling unit. We can run multi-containers in a pod. This container shares the network storage, etc. It seems to run on a local host and will be scheduled together by Kubernetes. We package the MariaDB instance, self-developed leader, and the actual program into a pod. When we create a group of pods through the MariaDB cluster controller, the MariaDB instance inside this pod has been started with the read-only start, and their leader components will communicate via TCP protocol. When one of the leader in MariaDB HA labeled pod acquired the lock, it sets the MariaDB instance read-write become the master role. Another pod leader notifies their MariaDB instance to execute the change master command to the pod. This leader component communicates regularly to update its states. Assume that the current master MariaDB instance is out of work. Another MariaDB HA labeled pod acquired the lock. Others leader receive the message and re-execute the change master command to new master instance. After the abort pod restart, the leader component received the event and execute the change master command to the new master. I prepared a demo video on my lab in advance, so let me show you. This is my lab environment that has a Kubernetes clusters. I create the MySQL cluster CRD name instead. You can see I create the MariaDB clusters. We can get the YAML file, the spec, the image, the spec we defined, like the LPS quota, the database resource, the CPU and the memory resource, and the master HA rep class number. And get the stateful set. The MariaDB class controller create two stateful sets, right? And the stateful set, the YAML defines the rep class number, the environment, the resource we allocated, and the PV will to mount the directory. So the two stateful set creates the each pause. We execute the pause, the bash, and see that the MySQL container, the leader container, they are into a pod. They show the namespace. And I want to show you the labels tagged to the pod. There has a key label. We label the DB role and label the pod is master true or false. And right now I killed a pod, the 010. We can show its master label is go away, right? The pod is in its state. And then we can hold a second. We can see another pod, another MariaDB HL pod. The label is the field is master equal true. And we labeled the is master equal true as related to the service, the headless service. Then we get the pod status. And right now we execute the master role pod. Going to the bash. Okay. And we'll go to the MariaDB and show the status. That is the master state. That is the master status. And right now we get the pod status to see another pod. Okay, it's start up right now. We go into the MariaDB pod. When they show the slave status, okay, it becomes the slave and change mask to the mask now and use through the service. Okay. Okay, let's go on. The Kubernetes, the backup MariaDB instance, the Kubernetes job can start a pod to do one's task. The backup pod container designed to run in Kubernetes as a cron job to perform actual backup of MariaDB to the S3 cloud storage. The recovering a MariaDB instance, we need copy a backup file from outside to a new pod. We can use the init container feature to initialize the MariaDB instance. Before the new pod starts, we copy the backup file from S3 storage to the new pod with the mount PV, and running extra backup program reload the backup files to recover historical state. And there has so many articles introduce how to implementation monitor system. We do not talk too much. while the logs are about a specific event. Metrics are measurable as a measurement at a point in time for a system. On Kubernetes, Prometheus is called native applications. Existing exporters allow bridging of third-party data into the Prometheus. The EFK is very easy to integrate into Kubernetes and supply log elections, analyzations, and exhibitions. The Helm. Helm is a third-party tool to deploy apps in Kubernetes, and Helm as like a apt-get or YARN under Kubernetes. It manages a complex collection of applications because our applications usually consist of multi microservices. Helm is very easy to upgrade or roll back the previous version if upgrade failed. Okay, thanks for your guys listening. If you have any further questions needed to be discussed, please feel free to email me or at my WeChat account. Many thanks.